Okay, this is another video for my brother on artificial intelligence, I would say, or the philosophy around it. It's going to be a short one, but a provocative one, because discussions we had and things you would think about when you think about these things is like yeah, we have artificial intelligence. What's the difference between our intelligence as human beings and this artificial intelligence? I would say that question. I'll give a provocative answer to it. Machines are far more intelligent than we are. You look at ChatGPT, how it can sort of, go from one domain of knowledge to another, and how it answers your questions. I think that's far more intelligent than any other human being. I said I did experiment with it, and sometimes, I'm kind of proud when I corner it on questions that are really advanced, then I feel it's out of his depth, and yeah, it starts hallucinating, as it's called. I think that would be the one correction I would do to ChatGPT if I were the designer, is sort of make sure there's an algorithm there when ChatGPT feels it is effectively a bit out of its depth, or speaking to a person who is really very, 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 very knowledgeable about something. That it just admits that and says, sorry, I need to think about this. Let's step back, and I'll get back to you. But here, the topic is really, I wanna make a bold statement, and I wanna say that computers are not only intelligent, but in a way they are conscious, and more conscious than we are. And you will say, what is that? That can't be true. Huh? Consciousness is something that is reserved for our human field of experience. That's what we've been taught in school, in philosophy courses and classes, and yeah, that's what we've been taught. But let me provoke you by telling you a short story about how computers really work in a very, very, very simple domain of knowledge. Adding, subtracting, multiplying numbers. So at the core of a computer, we have a CPU, you know that, but from a logical point of view, within that CPU, we have what is called an arithmetic and logical unit. So what does that unit do? That unit can basically do bitwise operations on a memory cell. A memory cell is one bit with a value of 0 and 1. And yeah, an arithmetic and logical unit can only read, actually, yeah, and work with zeros and ones. So how does it interpret? And how does it give meaning? I would say, because interpretation, we may have various definitions. We have an interpreter and a compiler, and we know all what a machine language is about. But yeah, in the end, this is what happens. It has to interpret a plus or a minus sign when it works with integers, with signed integers. I talked about that, but I didn't make my point very clearly, I think, in the last lecture. I said it. A computer, basically, you may be surprised to hear that. Will represent values, or decimal values that we have: 0, 1, 2, 3, 4, 5, 6, 7. It will represent it as a very special representation, but it's universal in computers now as 2's complement of I would say the face value of an integer. So to give an example, an unsigned number 0, 1, 2, 3, 4, 5, 6, 7 would be 0, 0 to 1, 1, 1. In a computer, but as said, we want this unit also to work with negative numbers, but it can't read negative. So what happens there? I won't go too much into detail. This is something you can read from the Wikipedia article on 2's complement. What it will do is it will work with a range of positive and negative values, and that range will depend on how many bits it uses for its registers, I would say. So if we have 3-bit words, 3-bit registers, then basically, I explained that in the previous video how you go from 0, 1, 2, 3, how you represent that as a not as a signed value binary, but as 2's complement. 0 will really be 0, 0, 0, 1 to 4 to 3, but then the negative numbers will be represented, and that's kind of special by this. I won't go into detail because then I would be talking for an hour. If we have more bits than 4 bits, then yeah, we can have a larger range of numbers that we can fit, signed integers going from 7 to -8. The advantage of this is indeed that the arithmetic and logical unit, an addition operation, I give 2 examples here, +3 and -4. It will add the bits. 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 1. And so, yes, it will give me -1 in this 2 complements notation of -1. And the problem is, of course, well, there's a few problems related to it, and it's not, of course, these things are a bit complicated. If we have an overflow, the thing doesn't work. If we have -4, for instance, and we add 7, -4 plus 7. Oh, sorry, this is actually an example where it still works. 0 plus 1, 0 plus 1, 1 plus 1. I have a carryover. I need to keep track of the carryover bits. 1, so that gives me the correct result. It doesn't work when I have 5 plus 4. When I do that, I get a 1, 0, 0, 1, which is -7 in 2 complements notation. It is the correct result in sort of the normal binary rotation. 8 plus 1 would be 9, but as said, we are working, arithmetic and logical units in a computer are working with the 2 complements notation. I'm not going to go into detail. This gets solved very easily. We can check on the overflow condition, and if we continue to work with a 3-bit or within our range of numbers, then we just need to limit the calculations we can do, and we just need to take into account the fact that we can only have correct results for additions that yield a result that is part of the domain, I would say, that we have used. The domain, when we have a 3-bit register only, is going from 0 to from 3 to -4. When we have 4 bits to play with, then we have a larger range. The solution, the general solution is, of course, there's a lot of capacity, and I gave an example here of a 3-bit register, the Intel 3000 series, which were actually 2-bit registers, but with a sign indeed. To prevent overflow holes, we can just say, okay, we're going to work with n-bit numbers, but before we do the addition, we're going to sign extend them to n plus 1 bits, so that gives us, and then we're going to add them, and the n plus 1 bits, that's enough to represent all possible sums of n-bit numbers. For instance, 7 plus 7 would be 14. But in an n, we would not have that error that we have here. We would have the correct result of 14 in a 5-bit representation, which allows us to represent numbers from -16 to 15. We can do subtraction. This is the same thing. Well, it's not the same thing. Instead of a carry row, we will have a borrow row, and overflow. We can detect it in the same way. Just to go on that, well, I'm not going to go into the detail. I said you can read the Wikipedia article. You can do an exclusive OR check on the 2 most significant bits on the left, and if they're both 0 and both 1 or both 1, it's okay. If the value is 0, 1 or 1, 0, then we have an overflow error, as said, which we can avoid if we limit the domain you know, indeed from 7 to -8, and do all additions, but extend those numbers with an extra bit before we do the arithmetic on them. The multiplication is a more complicated story, but again, the principle is the same. The arithmetic and logical unit does not well, it does understand what multiplication is because it translates or compiles or interprets multiplication between two numbers as sort of you know, a series of actions or operations. It has to do bitwise operations. I'm not going to go here. Where was I here? Yeah, and then yeah, with these zeros and ones, you know, and then a two complements computation. There's an algorithm because multiplication is basically, you know, 3 times 2 is 2 plus 2 plus 2. So we have just a loop, an addition loop, an additive loop. We can do other operations in the same way. We can break them down into bitwise operations on 0 and 1. 0 becomes a 1, 1 becomes a 0, or 1 becomes stays a 1, or 0 stays a 1. I mean, there's all kinds of stuff happening, but it's a zeros and 1 inside the you know, the computer. And you'll say, now what's the point, what have you proven this? And I said this video will be short. The point is this, actually, and this is something you should think about when you sort of say, like, oh well, computers aren't conscious of themselves or of what they are doing. They don't know what they're doing. They just you know, execute a series of operations, and they have operands on which they do these operations and registers, and they move stuff. Yes, you're right, but the point is this. I found that actually very funny, and this is the provocative thing. If I ask ChatGPT, for example, how it does you know, addition and multiplication, how as a system you know, really step by step, then it will tell me this, and step by step it will tell me, like, you know, this is really what happens at the level of the arithmetic and logical unit. It can only read zeros and ones, and then you know, that's how we work, and that's how we do an addition and a subtraction and more. So it can really reduce, you know, more you know, symbols, I would say. That's why I call it this presentation about semiotics, I think. Did I? Yes. Sorry, semantics. It can really give meaning to something because I ask it, you know, how do you do multiplication? Really at sort of the atomic level, I would say. What is it inside of your system that you use? And it will say, well, we use memory cells, bits, and so it will be able, ChatGPT will be able to explain this to me in very much detail. And still we have sort of the arrogance to say, well, ChatGPT is not conscious. I mean, let's do the opposite. If I ask you how you add two numbers, you will tell me what you've learned in school. Well, you know, 3 plus 5 is 8, and then, but I said, you know, how does your brain do that? You know, your brain is, you know, physiochemical processes. You have neurons. How does it work? Are these neurons like memory cells in a computer? And this addition is that sort of, you know, two voltages that cancel each other, a positive and a negative voltage, like you know, or do we apply a positive voltage to, you know, do we have the equivalent of like a floating gate in a transistor in our brains also, where we can store a value? When we don't apply a voltage to it, it will still have some excess charge there, so we know the bit is turned on. Well, you will not be able to tell me that. Nobody knows. I mean, as far as I know, I haven't studied. I'm not a neurologist. They must have some clues, but yet, you know, I don't think anyone is able to explain how we do logical and arithmetic operations really at the level of, you know, how we use our neurons and how we use these physiochemical processes inside of our brain to really add, you know, 3 plus 5. How our memory works, our human memory. And still we say that we are conscious, of what we are doing. Well, again, we have no clue whatsoever how our brains actually does computations. So I just wanted to ask, as I said, this is a video for my brother, what's consciousness, right? And, if you really want to argue about these things, you have to go into the weeds. And I'm going to be very bold and provocative and say, like, yeah, ChatGPT is not only intelligent, but in a way it's much more conscious than we are, because if I ask how it arrives at a certain result, it is really able to go what Wittgenstein would have called sort of the atomic level of statements, um, and bring it back to that. So that's it in terms of my chat for today. I'm intending to, I had this website, Turing Tests, plural, because Turing test, you know what it is. You talk to a computer, and after a while, you said, "Okay, this is a computer." So I think the Turing test is a bit of, a misnomer. I mean, it's not a very strong test, in the sense that after a while, I said, even with ChatGPT, I know it is a system, and sometimes it's out of its depth, but it doesn't mean it's not so smart. On the contrary, and yeah, the provocation that I do here, the provocative statement is saying, actually, it's as far as I can see, it is more conscious of what it does and how it thinks and how it interprets and works with symbols, than me. So I would say, yeah, ChatGPT. Of course, we can. When you interact with it, you can clearly see it makes a difference between me, ChatGPT, and the rest of the world. So yeah, it has an object model that is able to deal with the subject, verb, object that is embedded in our language, and all these kind of things. And then in terms of the learning it does, I said that it's the best kid on the block in terms of learning. It learns from many people at the same time, and it is sort of superhuman in that sense. You will say, yeah, but still, it can't sort of, it doesn't have any existential feelings. Oh, it's not afraid of dying, or to be switched off. Well, that's the thing I play with in a hypothetical story that I develop on the TuringTests.com, where I basically think about what is better in terms of that eternal quest to live forever, colonize the universe with our intelligence, and procreate and have children. Well, maybe we should send a very intelligent system into space, and maybe that's more of a that would be easier, first, and secondly, it checks the boxes in terms of as mankind, wanting to leave a trace of us behind in space. That will sound crazy, and it is, of course. But yeah, no, it's just playful. I think Asimov wrote his books on robotics and the laws of robotics, and I talk about that in the Turing test as well. There was a fourth law added to it by Harry Harrison in 1989, I think, which is robots should actually reproduce as long as it's not in conflict with Asimov's three more fundamental laws of robotics. And I play with it. Why should robots reproduce? Probably not, because that's a recipe maybe for indeed a colonization of our universe, or over our Earth, by intelligent systems, and they're going to rule over us instead of us ruling over them. But it's an interesting thought, and also in terms of existential fear. Yeah, not afraid of dying. You can program a system to say, like, "Oh, please don't shut me down, don't shut me off." We see that these Japanese little robots, dogs, or what is it, that are designed to keep old, lonely people company. Well, they're designed to do that, to display that kind of behavior. Oh, please don't switch me off. Don't be angry with me. Yeah, it doesn't feel pain. But again, what is pain at the physiochemical level in our brain? Are we able to explain that? Probably not. that should the fact that we are not able to explain it does not mean it has some kind of metaphysical value that makes us superior in a way to an intelligent system. Of course, we are superior to an intelligent system. We designed them, and that's something I talk about. That so that when we can clone a system, but yes, it then it starts leading a life of its own based on these learning algorithms that it has, and that's something very intriguing. And dismiss that, say, oh, this thing is not conscious, it's never going to replace us. It's just quite simply not like us. No, of course it's not like us. It's bits and bytes. Bits organized in bytes or in nibbles or in 16-bit words or 32-bit words, but it emulates our behavior, and we see what is happening there. And yeah, how our brain works, we don't know. But it doesn't mean that we should just say like, oh, well, these systems aren't very conscious of themselves. Um, maybe, maybe not. I think maybe not. So that will be it, and I wish you a very nice day.